All right, so today we have with us Jeff Clark, alum of the music technology program at Georgia Southern University. He is a music technologist, a conductor, composer, music theorist. He does all of those things. Um, he's going to speak to us today about spatialization techniques with a particular focus on ambisonic techniques. So, how do we move sound around in a recording, and what are different ways that we might use that technique to our advantage in the music technology world? Jeff is an Emmy award-winning technologist. So congratulations on your Emmy awards. All right, with that, I'm going to turn it over to Jeff.
Hello, everyone. Um, spatialization is a crazy field to work in. I've been doing. I did spatialization when I was there at Georgia Southern. My master's thesis was actually on a certain subset of ambisonics techniques, and then I've actually done some spatialization here. I recently got a paper accepted in the ICMC dealing with the spatialization of non-point sound sources in virtual reality. And there's so much to learn and so much to do because every application of audio kind of has its own weird demands. Like there's entire books written just about the math and theory and everything just behind stereo spatialization. It gets crazy. One of my favorite techniques that I always kind of come back to is ambisonics. It's very flexible. It's very useful. And the theorist in me always loves all the different thought exercises that you can sort of tease out of it. So that's what I'm going to mainly focus on. So let me know if you have questions as we go on. I have some audio examples I'll show, but unfortunately, I think I'm just going to do a lot of talking because ambisonics is weird. So in discussing any sort of spatialization technique, you first have to define what space is, which from a mathematical standpoint can get very fun because if you try hard enough, like a 5.1 sound system actually exists in four-dimensional space if you try hard enough. It's wild how computers can think of things and how we have to describe things to computers. And so when we talk about sound spatialization, the biggest thing we're looking for is how we find a point in space. And this whole current trend of 3D sound, which I hate that term beyond belief. It's so hard not to start ranting whenever I hear it because it's such a misnomer in how we throw all these things together. We talk about 3D sound as being 5.1 plus height, all the way to 6 degree of freedom virtual reality, and it's all 3D sound somehow. And so I think it's worth kind of coming back to what does 3D mean. And so normally we talk about dimensions. We think of Cartesian space and the Cartesian sort of dimensions as we name them, which is length, width, and height. So this bottle of delicious healthy soda I have, the bottle is so long, it's so it has these three spatial dimensions, and it's a physical object I can hold in front of me in space. It's right here in my hands, and soon the contents will be in my stomach, as happens. And we're used to this is how we visually see things. The speaker next to me is over here. It's 3-ish feet away. It's about a foot above me. We describe these things in terms of these distances. But it's an important thing to consider when we talk about sound spatialization. Do we hear in Cartesian space? And this is the crux of why I hate the term 3D sound. So how do we hear sound? We don't hear distance. We hear our perception of loudness, which is this really, really messed up psychoacoustic phenomenon that we keep chasing with all these perceptual studies and trying to nail down all the fun nonlinearities of our perception of loudness. And we don't hear, the length, width, height of the sound. We hear its direction. We can sort of point in the direction of a sound or wave our hand ambiguously. It's sort of over there, kind of. and it's, really loud, it's not quite that loud, so on. And that sort of representation doesn't translate well to this length, width, height idea, because that's not how we can describe sound from our experiential point of view. So if you remember back to trigonometry, and I apologize for the upcoming trig review. No, I don't. This is this idea of being able to point in some angular direction. It's, roughly 45 degrees that way and about 30 degrees up, is reminiscent of polar space. We have some sort of polar coordinates represented in angles. And so the two angular coordinates of polar space are the azimuth, the horizontal deflection, and the elevation, which is our vertical deflection. It said 45 degrees over, or I guess that speaker I keep pointing at is 30 degrees over, and 20 degrees up, right? Azimuth, elevation. And then the third component of polar space, the third dimension of polar space, so to speak, is magnitude. And when we start talking about how we represent magnitude in polar space in terms of audio, this gets to be kind of counterintuitive for a lot of people, because we have to understand what magnitude is. And when we're talking specifically about sound spatialization and ambisonics, where we really are representing things in polar space, magnitude is analogous to the magnitude of the wave, the magnitude of the amplitude. And so it's worth remembering that when you see graphs of these things, a longer line is not more distance or further away. It is a stronger, a higher amplitude signal. That counterintuitive in seeing the point further away actually signifying something louder can seem counterintuitive for people. So if we think, the azimuth, the elevation, we're pointing in some direction, it's over this way, it's up this way, and it's kind of this loud, however we interpret loudness. And of course, with microphones and transductions, we can actually get a fairly exacting amplitude to represent in the computer. We can represent the sound in polar space. So how do we find this point? How do we represent it? Well, trig review. If you remember, if we think of a circle, a unit circle around the origin, right? Our x deflection can be found by taking the cosine of the circular rotation. And our change in y can be found by taking the sine of the angular rotation. So this means that if x is equal to the cosine of theta, which is our angular rotation, and y is equal to the sine of theta, then our vector coordinate xy is equal to our signal, our audio signal, times the cosine of theta sine theta. And if you don't know vector notation, if you want to do anything in sound spatialization, get comfortable with it because it's everywhere. This is not. I read so many papers in this field with the calculus textbook in one hand and the paper in the other, because you can't avoid it. Especially when you start talking about higher order ambisonics, you go into the weeds with VBAP and things like that. It's interesting. It's useful, and getting some of the nuts and bolts behind these things can be really powerful, but there's a learning curve.
Just to make sure we understand what we're looking at, here we have a vector of x and y.
Right.
And we're saying that the cosine of theta here corresponds to x, correct? So this wouldn't be correct if we put sine of theta on the top here. Is that true?
Yes. Okay. Now, where was I? Right. So if S is some number that we're putting in, then we can find its point on the circle, how rotated around the circle S is, which is the azimuth, by taking our sine and cosine functions will give us the plot of xy. There's a problem. This only works if S is a positive number. Because if you remember, as you pass your 90-degree rotation, depending on which way you're rotating from, your sine, your cosine is going to pop negative. And having taking a sound to -1 just flips it upside down. And we run into this issue of having to know which way right side up is. As an example, which of these two sounds is right side up? With a lot of machine learning and feature extraction and so on, you might be able to automate it and figure it out, but it is not worth the computational power you would spend doing this. And you would end up with all kinds of spectral bleed, artifacting, and so on, trying to extract and reconstruct the phase rectified sound from its direction. And there's a much simpler solution for dealing with this problem of negative numbers in our sound. And that is simply to add what we call the W channel, which is a 0th order coefficient, which is the the polarity rectified version of the sound. So the W channel records every sound in its positive polarity orientation, so that we know basically which direction up or positive is on both of our axes. Now, the traditional way to think of this is your X and Y axes can be represented as two bidirectional microphones facing 90 degrees apart, with, of course, whichever axis you want to be forward is forward, and then the other one facing traditionally left, but it really doesn't matter as long as you know which one's which. And then you have an omnidirectional microphone, your true pressure microphone that captures the polarity rectified version of the sound. Because from a bidirectional microphone's point of view, sound that is compressing at the front of the microphone is the same as sound that is decompressing at the back of the microphone, because it'll flex this way. So from the front, I'm pushing, which is the compression in the air. But if this plane wave is coming from the rear, then this appears to be pulling, which is your negative pressure zone. So the W channel, where compression is always compression and relaxation is always relaxation, will tell us which way the sound was coming relative to each bidirectional component. And in fact, you can build a microphone array on this principle. The omnidirectional microphone and then the two bidirectional microphones at 90 degrees apart is referred to as a Nimbus Halliday array and is used by Nimbus Records in UK, which is the oldest record label that issues ambisonics format CDs. I think they're still doing CDs now. And they have a special format I'll talk about later as to how they do that on the CD. But that's how they record it, is they use a really high-end omnidirectional microphone and then two ribbons at 90 degrees. And that's how they get their two-dimensional ambisonic format. And they just sort of slice that second dimension across the ensemble. But again, you notice we only have the X and Y axes. We don't have our height. We don't have Z. So there's no elevation in this. So we need to expand this, of course, to our third dimension.
Can I pause you for a second there? I just want to talk about the W and XY. So we had X corresponding to cosine of theta and Y corresponding to sine of theta, which we've already discussed. But here we have W corresponding to 1 over the square root of 2. So what does that correlation mean for us?
In the ambisonics format, there are a whole... you run into the issue that as you start adding these things back together, that they can... The W channel and then your matrix, however many extra coefficients you have, and that number is variable, as we'll discuss. You want them to be roughly even. And, there is this whole scheme of weighting coefficients, both on the W channel, which is what that 1 over square root of 2 is, and then on the X, Y, Z, and however many other letters you're going to use, to make sure that when you matrix everything back to get your sound at a particular point, you have the mathematical accuracy you're looking for. And so the 1 over square root of 2 is to help balance the W channel against X and Y when everything gets combined back.
Okay, so basically it's just attenuation, right? So we're taking the sound down by whatever that number is, which I think is it 0.707?
Yeah, that's going to be about 3 decibels.
Yeah. So we're just turning it down. That's what that means. Okay.
And yeah. Um, so going into the third dimension, we add our z, and this is where we need our elevation. And so in a lot of the literature, you'll see all kinds of Greek letters used. It's usually a pair of Greek letters, and most of the stuff I've seen, I'm going to say these words cautiously, most of the stuff I've seen, your azimuth, your horizontal deflection, is represented with theta, which is the circle with the line horizontally through it, and elevation is represented with the Greek symbol phi, which is the circle with the vertical line. Um, and so we just expand our matrix so that our horizontal sine cosine relationship with x and y is now includes our sine cosine relationship with z, which is our vertical pointing axis. And it's just a simple transformation matrix. I promise it's not as terrible as it looks. And we have computers to do all this for us.
So just so we're totally clear, like what we're looking at, right, is how we would embed in a signal the location of the signal, right? We just simply multiply the signal by this vector.
Right.
And that embeds in the signal its location.
Right.
So, but what unit is the location? Because, you know, in a stereo, it's what percentage of it is coming out of the left or the right. So I just don't, it's hard for me to, I guess I should have put this in chat. I'm sorry.
No, it's good.
What dimension is this really, you know? And like, is it different if we're calculating 1 meter sphere versus like 100 meter?
So this is one of the failings I'll talk about more in depth in a second of ambisonics is the sphere is functionally infinitely small. And that goes into a whole host of listening issues. But to answer your question, the azimuth and the elevation, if you think of a physical sphere and it's pointing forward, right? Then the azimuth and elevation are simply degrees of rotation pointing out of that sphere. So I would want to set the azimuth and elevation so that they're pointing at the sound source from my reference point. So these will either be degrees or radians. Most computer like processes like this, like if you're doing this in max, you're going to have to use radians instead of degrees. But these are simple angles. So 2 pi radians of horizontal rotation, and then negative pi to positive pi of vertical rotation.
Okay, that's an interesting thing you said there, because that makes a lot of sense. That what we're doing now is just defining a vector from the center of the sphere. We're not actually saying what the location is, because we don't know the magnitude, for instance. So we don't know the distance from the center. We just point in a direction where we think the sound is coming from.
Right. Because the magnitude, what would normally be the distance of the sphere, is the signed amplitude of the sound. So in some ways, you think of when you're representing the sound, what we're looking at is the texture of the circle. So the further the circle out is at any point, the louder the sound is in that direction. And that's what we're comparing is loudnesses and directions, which is it gets to be, like I said, very abstract. It's fun. There's definitely some mental.
Sorry, I
goes on.
A little comment, if that's okay. Following Ryan's question, I think, well, at least what I understand is that we're figuring out just more of a coefficient that then we can multiply an amplitude to, right?
Right. So in this case, s being multiplied by the vector, the s would be the amplitude that you're encoding. Because actually, you can represent a stereo panner as your left speaker being the sine of theta and your right speaker being the cosine of theta. And if you just constrain your panning to the positive quadrant of orthogonal axes, so you envision your two speakers, your left and right, as being at a 90-degree angle instead of a 60-degree angle. That's actually how a lot of panners end up working. Is the same sort of methodology, just constrained to a quarter circle between your X and Y axes. Did I answer your question, Ryan?
Yeah, I think so. I just
Okay.
I'll keep listening because I think it'll start to be illuminated as we see how it fits in with the samples.
Yeah.
Maybe it's also important to note that this is not a 2-channel file in any way at this point. So for each coordinate of the vector, or each, what do we call this? For the W, X, Y, and Z, that's a different channel of our signal. It's a 4-channel signal right now.
Right. And the channels don't actually correspond to any real outputs. Ambisonics and some other similar formats are what we call intermediate formats, in that they represent a description of the spatial characteristics of the sound at a particular point in space. You then have to sort of flip this thing inside out and project it back onto whatever speaker array you're using. Which, let me hit the next slide because I think some of this will kind of begin to make sense. Slide, maybe. So when we talk about stereo, we talk about a channel-based format, and in channel-based formats, each audio channel corresponds to a physical output. So this is going to be your stereo, your 5.1, your quad, a binaural output. The 8.1 that you use for root signals. Every audio channel in your file is mapped directly to a speaker, and so the space of the spatial characteristics of the audio are defined by the output speaker layout. Ambisonics is what we call a scene-based spatial audio, and in this case, the audio channels describe the spatial propagation of the audio through a point. So in the case of ambisonics, we're looking at the sound in terms of like being drawn on a sphere, and then sort of pointing at the sound through the sphere. Another format is called Mach 1 or SPS, which stands for Spatial PCM Sampling, which uses a mesh of points that, how do I say? It's basically an equitriangular mesh of speakers is how it sort of envisions everything. Anyway, in C-based audio, you're describing the sound field at a particular point in time in a very abstract format, and that's the sort of the hard thing the thing that takes time to understand about these is because it is abstracted in some way. In ambisonics, you're talking about spherical harmonics, decompositions of the sphere into its different polynomial descriptions. In SPS, you're talking about a whole bunch of phase vectors and the encoded magnitudes of each of those vectors. And the final one is object-based. In this case, your audio channel plus your metadata, it describes the sound source. So like when you're panning a DAW and you have a mono signal coming in and then you have your panning knob turned some way, the audio signal plus the metadata of the panning knob can be used to describe where that sound is going to be in the 2-channel field. But if I have that and I have 5 speakers across the front, I can resynthesize that data to equally pan across the 5 speakers. And this is this is how like Atmos works. This is how a lot of 3D game audio works. Is you have your sound object that exists somewhere within the virtual space, and by knowing what sound is tied to the object and where in the virtual space it is, you can then do your processing. And in fact, in a lot of game audio engines, they use ambisonics as the intermediate format to go between the game objects emitting their sounds and then encode it into whatever the output format of the video game is going to be. Whether that's a channel-based format, stereo, 5.1, headphones, whatever. Which becomes the utility of these scene-based formats is the way that they're very easy to translate between different speaker configurations. And some EA composers will do that. They'll write a piece and they'll code it into an ambisonic or an SPS or some type of format like that. That they can then say, okay, this concert's going to be on 5/1, kick out a 5/1 format very quickly by just sampling those particular vectors where those speakers are going to be, and then okay, this next concert's an 8/1, so I sample the equal angular 8-channel array out of the intermediate format without having to completely redo my panning and my routing and everything else. So as I said, ambisonics is a scene-based format. And because it's a scene-based format, our channels, as we pointed out before, don't describe actual outputs. So we have to decode ambisonics. And each, and the sums of these channels represent audio as a spherical wave. Now, one of the interesting things I find about ambisonics and where its utility kind of expands is this idea of sound as a radial wave can actually be thought of as the radial wave collapsing in on a point, all of the sound through all the vectors around it collapsing towards a point, but also you can also flip it again inside out and think about all the sound being emitted from a point. And this actually gets used a lot in acoustics research. But some of the pros of ambisonics, it is scalable through increasing orders. So we talk about the W, X, Y, and Z channels as the being analogous to our X, Y, Z axis, if you remember your right-hand rule. We can increase our angular precision. So in ambisonics, if I can emulate a standard cardioid microphone in an ambisonic sound field. If I increase the order, so if I add more spherical harmonics that give increasing resolution, I can actually get down to very idealized shotgun-style microphones that don't have all the weirdness and side lobes and everything that a real shotgun will. And if I don't need that, then of course I don't have to have those things. So your angular precision, how tightly you can define distinctions between those vectors, is very easily scalable. The other nice thing is that because we're representing sound as a sphere, we can freely rotate the sphere. This is why for binaural things, for things with headphones where they're doing head tracking, you almost always see ambisonic as the intermediate layer, because you can start with everything just facing forward, let the sound hit it, and then if this person's head's turned, you can take that sound field and then just turn it to match their head. Or sorry, you didn't turn it against their head. But the ability to rotate the spherical harmonics is very well mathematically defined, and it's very computationally efficient because it is simple trigonometric identities.
There's a question in the chat that says, why not always use the highest order? So what are the downsides to higher order ambisonics?
I'll get there, I promise, because that is one of the downsides to things. And of course, ease of translation I was talking about is that you can start with an ambisonic sound field and you can kick out just about any actual channel-based format. And you can use ambisonics to re-encode between formats. So some of the cons. There we go. Some of the cons is the minimal sweet spot. As I said, especially if you're talking what we call first-order ambisonics, which is the WXYZ that I described, your sweet spot tends towards being infinitely small, which is not great because the human head is not infinitely small. So when you're talking about loudspeaker reproduction, in terms of sound fidelity, ambisonics is actually usually not your best choice unless you are working at a very high order. Because of this sweet spot issue, by somebody moving their head just a little bit too much, it can throw off the sound spatialization. Because of everything being recorded at a particular point in space, ambisonics is very phase reliant. This is one of the things that I experimented with in my master's project. Was how decorrelated two microphones needed to be from each other for them not to screw each other over when you mono-encoded them both into the same sound field. If you have phase discrepancies between two microphones in the same room, that can cause steering issues at certain frequencies when they become prominent. If their period is equal to or less than the travel time between the two microphones, and there's not enough attenuation from the distance between them, you can suddenly get a sound that'll sort of scoot towards the other microphone under certain circumstances. And then going back with the sweet spot thing, because of how we do the decoding, the angular imprecision, you get a lot of spectral bleed. You get a lot of antiphase information when you do your decoding as you try to become more angularly precise. And this is, of course, all dependent on the order. If you use a stupidly high order, a lot of these cons go away, but then you're using CPU processing power. So first order ambisonics is 4 channels. And to give you an idea, second order ambisonics scales up to 8 channels, and third order scales up to 16. Or is it? I think it's 7 and 16. Anyway, it almost doubles the amount of channels you need every time you step up an order, which becomes the reason to not always use the highest order, because if you wanted like a good listening sweet spot, you're at 5th order, and if third order is 32 channels, you can imagine like how nasty that's getting on your computer to have to compute that many channels for all of your ambisonic processing, especially if you're doing mono-encoded sources where you have 32 plus channels for every individual source you're panning in space. The DSP requirements become really heavy really fast. The sweet spot, for those of you that are curious, tends to be between 3rd and 5th order, depending on how much processing you're doing. Most audio plugins, like Google Resonance, DearVR, Blue Ripple, Rapture 3D, they tend to max out around 3rd order, because that is kind of the point of diminishing returns for a single person's listening perception versus the computational amount of power you need to go above 3rd order. I don't think I've seen anybody doing real-time audio above 5th order for anything that wasn't like a obscure research purpose. So some of the fun use cases that we see. So of course the obvious one of describing an audio scene, and of course you can do this with mono-encoded sources, but there are also sound field microphones, and I'll show you pictures of some and actually recordings of some here in a second. There are sound field microphones that you can actually put at on your soundstage, and they will capture an actual usually first order ambisonic signal at the microphone. And then there's a number of fun processing techniques you can use to do different things with that that I hope to demonstrate if Reaper's cooperating with me. And as I mentioned, and this gets used a lot in acoustics research, is capturing a radiating spherical wave. There's actually a very large database that I referenced in a project that I did, where they went into an anechoic chamber and they set up basically a sphere of microphones around the musicians, and they captured the sound of the instruments from basically every angle around it. And they encoded this information into a set of spherical harmonics. And so in the database, you can figure out, what the directivity pattern for any given frequency, and they were using 3rd octave bands, is in any direction just by calculating out the spherical harmonic for the vector that you're looking at. And I think their database was at 7th order, if I remember correctly, but that wasn't for real-time processing. And so you said I've actually done some experiments with similar things, trying to figure out the directivity of specific instruments and so on, using the same technique. It's actually a very helpful technique to have in your back pocket for getting information off of instruments as more than just a single point source aimed in a specific direction.
So let me make sure I understand that correctly. So someone has conducted some experiments
Mhm.
to be able to know with particular instruments. Now, there's a database about what the uh, spectral, I guess, directionality of the instrument is. Is that correct? And then how do you use that database? Like, is that something that you use like a head related transfer function, or is it something you read?
That's yeah. So that's the beauty of the spherical harmonic format, is that you could actually convolve it with a head related transfer function, although you'd want to pare the order down to something you could real time process. Or like what I was doing, I retranslated it down to use fewer spectral bands and with lower angular precision, because I was doing real time processing. And in the same way that we can look at the sound field and point out of it and grab the sound where the direction we're pointing intersects with the sphere. We can do the same thing here. That as we look outside the sphere represented by their measurements, we get a value that is some amount of attenuation of that frequency band in that direction from the instrument, because instruments don't radiate well. Yeah, no real instrument is going to radiate its sound perfectly across the entire frequency spectrum in every direction. There's always, some frequency bands will go better in one direction, not so well in another, and so on. And for some instruments, it gets really complicated, and it starts to depend on the particular note that's being played, or the amplitude that's being played at. And so, you can there's a number of visualization techniques you can use. You can actually graph any particular data point, so you can see how a given frequency radiates away from the instrument as a three-dimensional graph. And in this case, again, the further it goes away from the origin in a particular direction, the more it radiates in that direction. So there's a number of interesting ways you can use this. But as I said, I have found it useful to just sort of have in my mind as a data capture storage format, that you can use this format to record sound that's radiating away from a point, not just towards a point. Any other questions? Did I answer your question or comment?
I think I've got it.
Okay.
I guess I'd have to see what this database looks like. But I guess my question is: it something that you read as a human, or is it something that you don't read as a human?
The data. I don't think anyone would be able to just look at the raw database and read it as a human. I think you would need to apply some sort of transformation matrix to get out, human readable values. Especially because we're not used to thinking in polar space is hard enough for us to a certain extent, and then trying to think in complex decompositions of polar space is really hard. So the last use case, and one that I've been exploring more recently for a lot of things, is using sound field capture techniques as variable directional microphones. And this, to me, actually has some of the more interesting uses of ambisonic microphones themselves. Yeah. So talking about an audio scene, I kind of go through all these. We can describe things as an ambisonic sound field using an ambisonic microphone. We can mono-encode sources. And one of the things we run into is this issue of formats. And yeah, this is where a lot of the gotchas in ambisonics happen, is in formats and standards, because there really haven't been any. Ambisonics has been around for a very long time, longer than we've actually been able to do anything with it. Yeah. And so a lot of formats and nomenclature have evolved in weird ways, and some of them nobody uses anymore, but if you read an older paper, suddenly it's all over the place. So two of the formats we hear a lot, first off, is the A format. And so the A format is the actual raw output of a tetrahedral microphone. In a tetrahedral microphone, it is, It is what it says on the tin. It's a microphone that has 4 elements arranged in tetrahedron. And these are cardioid elements, usually highly calibrated, and they capture the sound as plane waves that come in from their aimed direction. And then there's a translation matrix that's used to encode those plane waves into our ambisonic spherical harmonics. Typically, most of the mic manufacturers who make these tetrahedral microphones will supply you with a plugin that does the translation for you, so you don't have to think about it. So unless you plan on building your own ambisonic microphone, the A format to what we call B format conversion is taken care of for you. And the B format represents your spherical harmonics domain. And so usually we're talking about ambisonics, we're talking about B format. Although there is some argument that B format should only apply to first order ambisonics and higher ambisonics should be something else. Usually when people say B format, they just mean like what we think of as actual ambisonics. There's a fun arrangement of B format called UHJ, which is actually a B format that's folded down to stereo using a phase rotation matrix. This is what Nimbus Records that I mentioned earlier does. And they'll use like Hilbert filters or some other 90-degree phase rotation filter to matrix the rear of the field into the front. And if you have what's called a UHJ player, it'll actually be able to dematrix everything out, and you can get the 2-dimensional sound field back out of the stereo signal. It's really obscure. It's fun. I've played with it. And there are most ambisonic releases that you find on CD or so on are in UHJ format, but there aren't a lot of them.
I have a question about this.
Sure.
So the UHJ format, B format folded down to stereo using phase rotation matrix. Mm-hmm. So that means that we can unfold it, right? So if I wanted to, could I play a UHJ format on multiple speakers?
Yes. You can, in theory, I'll use those words, in theory, you can recover the original 2-dimensional, because it's going to be a flat circle instead of a full sphere, the original 2-dimensional B format from a UHJ. But of course, when we're talking about 90-degree phase rotation filters, if you can actually, if your filters are good enough to encode it properly and to decode it properly without steering issues, is always the question. But in theory,
could you talk a little bit about phase rotation here? Because we're not talking about just delaying the sound by a certain amount. We're talking about every frequency has to be rotated by 90 degrees, or
yeah. So what they'll do is usually, I think it's called a Hilbert filter. I think Max actually has a Hilbert object that does this, and it's an all-pass filter that performs a phase rotation and then group delay compensation, so that you're changing the phase of the waveform by 90 degrees or pi over 2 radians, but you're doing it in a way that doesn't actually create a delay. It's to me, it's kind of wild that we're able to do that, because we think of we tend to think of a phase as being locked in time, but this is one of those cases where we can actually do arbitrary phase rotation without having to manipulate the time domain directly. I think that's the right spelling. Hilbert filter. And the object would be lowercase h. Misspelled it. Anyway, it'll be Hilbert with the tilde because it's a signal rate object. Oh, is it 1L? I don't remember. Anyway, I know Max has an object because I've actually built a UHJ encoder decoder. It was for one of Thompson's classes actually. I think it was in the MSP class. And it was fun. I remember using the Hilbert object to make it go. And so the last one that you'll occasionally see, it's really rare, is what's called G format, and that's just decoded ambisonics. That means somebody has taken the ambisonic sound field and has projected it to some speaker arrangement usually 5.1, sometimes quad if it's older. Occasionally you'll see the term G format around. It's rare, but it exists. Now we're talking about formats, even more formats. So we talk about, A format and B format, which tells us what the audio is. Are we talking about the output of a tetrahedral microphone? Are we talking about actual spherical harmonic coefficients? But one of the issues we run into is, what is channel 1? Like, which spherical harmonic is channel 1? And then we also run into that issue of the weighting of the coefficients, so that as we sum them together, we want to make sure that, when we decode our sonic sound field, that the output isn't greater than 1 and we end up clipping where we shouldn't be. So the sort of the OG ambisonics format is the first Malum format, or abbreviated FUMA, a lot. Don't use this. This will cause so many compatibility issues because the current ambisonics world has gotten so far away from this format. The channel numbers are wrong. The weightings are wrong. Like, none of your modern plugins will work with this format. But if you have older stuff like original soundfield equipment, like here at Ball State, we have an old soundfield microphone with the hardware 1RU decoder, and that kicks out a FUMA signal. So, it's one of the things you have to keep in your mind, that, like, you have to know when you have this, and there are a bunch of converters out there that will take you into the modern standards. So the channels are given letter names. Of course, you see me use letter names because when you're talking about first order ambisonics, letter names are easier to think about because they correspond to, X, Y, Z axes. And there's in FUMA notation, first Malum notation, goes up to third order, and there are letter names for all 16 third order channels. And then we're talking about the weighting coefficients. You use what's called max-in normalized weighting coefficients. The standard that we use now, in as much as there is a standard, is the Ambix standard. And the channels are numbered according to their legerdemain polynomial numbers. And if that means nothing to you, don't worry about it. Just know that it is a very different channel ordering than FUMA. And that's one of the bigger issues you'll run into if you accidentally send a FUMA signal into an Ambix processor, is your sound field will be rotated in a very weird direction, and also kind of, I think one of its dimensions will end up inside out. It's great fun. And it uses semi-normalized weighting coefficients, which is a different weighting coefficient scheme. Nice, as I said, the nice thing is all of these numbers are known. You can look them up. You can use an SN3D weighting coefficient table. It'll tell you how to do it. And there are a ton of VST plugins and Max objects out there that do all the translations for you and handle all of this, so you don't really ever have to think about it, which is lovely in practice. So, building an audio scene. One way to do it is to mono-encode a whole bunch of sources. This is from a picture I took after I unplugged all the microphones, and then I realized I should have taken a picture of a recording I did where I was doing a forced perspective piano recording reminiscent of one I did in my master's, where the audio listener is basically sitting on the soundboard of the piano, and I built the sound field around them with all the resonances of the soundboard sort of coming up at them. Yeah, $20,000 picture. There's mics to be careful with. The other route, as I talked about ambisonic microphones, is a tetrahedral microphone like this one. This is the Rode NTSF1. This is a great entry-level ambisonic microphone. It costs just shy of $1,000. And I know just $1,000 is a lot for us as grad students. But as microphones go, especially as high-end precision microphones go, that's not bad. And if you look at the actual cost of getting into any of the other ambisonic microphones that are actually like worth having, this is cheap. Very much so. Thank you. And so using this microphone, you can capture all of the sound coming at the microphone from every direction immediately as a sound field. And you can do a number of things with it. This is a picture I did capturing the radiospherical wave away from the instrument. So in this case, I was looking at the planar radiation characteristics of the harp. And you can see all those wonderful microphones sort of ringing it at two different heights. And that was what that was for. And I encoded that data as two flat sets of circular harmonics.
Can I pause you for a second there? And I'm curious about this. So here
Sure.
in this particular instance, we've got lots of microphones around.
Mm-hmm.
They're not following the 3-to-1 rule.
Right.
So, and when you say you're encoding this somehow, what's actually happening? I mean, what are we doing here?
Sure. The microphones that are immediately on the harp that are following the 3-1 rule were actually used for audio. The microphones that were ringing it, I ran into MATLAB, and I was looking at the frequency domain plots of each microphone and looking at the differences between them to see how the frequency spectrum changed in these different directions away from the harp. And then I used that to build a set of adaptive filters so that as a listener in virtual reality walks around the harp, I'm able to linearly interpolate between the filter coefficients so that it represents the actual directivity of the instrument in that direction that the listener is standing in.
Okay, so these microphones that are distant from the harp are
Yes.
not actually sound sources, right? They are just informing an algorithm so that if someone were to virtually walk around this harp, that the frequency-dependent spatialization characteristics would be correct. Is that right?
Right. So yeah, the microphones that are way off the harp were used for frequency domain data collection and analysis, and not for actual sound. And this is a technique that I borrowed from some acoustics literature. It works far better when you have an anechoic chamber. I will say that, or a significantly larger room. Reflections in this room really did a lot to corrupt the data, but you work with the spaces you have. So variable directivity microphones. This is one of my favorite techniques, and that fun equation staring at you is how you get a microphone of some arbitrary polar pattern out of a sound field. And this is why we have computers, so I have to think about these things. So what you're looking at is these four variables. Your S, which is of course is your signal. That's not S. What am I thinking? Sorry. That's wrong. Wow, I was thinking two different things when I wrote this. The equation's right. It's just S. S should be W. I'm sorry. That's the only change. S should be W. So P is your directivity coefficient, or if you think of P as polar pattern. And all you're looking at is P of S, which again should be W. W is the whole sound field. It's the entire sphere considered as one coefficient. And you can think of that as the omnidirectional microphone. So if you remember, you can get cardioid pattern microphones by adding an omni and a bidirectional microphone together. So if you look at the plus sign, the PS, or which should be PW, is your omni microphone, and you're adding it to all that mess on the other side, which is your bidirectional microphone. And all P is doing is it is waiting between the omni microphone and the bidirectional microphone. It's simple linear interpolation between the two. So if P is 1, we would expect to get all omni, and then of course everything to the left would be 0, so no bidirectional. And then if P was 0, we would get no omni, and then of course 1 minus 0 is 1, so we get everything in the bidirectional microphone. And then all that mess, wow, I had some serious typing errors. That first Y should be X. Man. That's what happens when you get in a hurry. So you're just taking those coefficients and the angle of the azimuth, and now it's the angle of the azimuth that the microphone from the sound field is aimed in. So whichever azimuth the microphone's facing in, whichever elevation it's facing in, and then you just multiply those things by your X, Y, and Z coefficients, and you pop out with whatever a microphone aimed in that direction would capture.
What is M? What is M in this equation?
Microphone. It should be M of P theta, whatever. M of P theta phi. So the nice thing about virtual microphones out of the sound field is if you start drawing multiple virtual microphones, they are phase coherent. They do represent actual coincident microphones. It's not almost coincident. It's not nearly coincident. They are, in fact, perfectly coincident. And then, of course, in this case, directivity depends on P. P equals 0 in this case would give us a bidirectional. P equals 1 would give us omni. And then P 0.5 would give us a cardioid polar pattern. And so one of the big uses of this is that we can use two virtual microphones to emulate ideal coincident pairs. That was one of the things I wanted to show. Of course, we're not getting stereo, but I can at least show you what it looks like. So this is a plugin that's made by Blue Ripple Sound. This is from their O3A TOA Core series. And all this plugin is doing is kicking out a stereo signal based on a stereo pair in a B format. So I'm sending, if you look up here, this 4-channel signal into this plugin. And I can define the stereo width, the stereo width of the two microphones, and between omni and bidirectional. And as we see here.
So the original signal has to be done with a sound field microphone, right?
Yeah. So this original signal, and actually this original signal is actually an A format signal here. The plugin in front of it is the encoding plugin. Come on. That's made by Rode. Did Reaper just crash? This may be the first time Reaper has ever crashed on me.
That's the first time for everything. So by virtual microphone, we're talking about creating out of a sound field microphone virtual microphones, right?
Right.
Okay.
Let me see if I can reopen Reaper. You have to do the waiting because I need to pay Reaper their money.
While Reaper opens, I have a question. That sound file that you said that you used a field microphone to record 4 channels. Which type of field microphone was that?
It was actually I think the specific one I showed you in that picture a couple of slides ago. So yeah, here we go. Oh, that's what that one. I know I have this plugin. I made the session on the same computer. I don't know why it's crashing. Wow. Reaper is not having a good day. Anyway, there's a plugin from the microphone manufacturer ahead of that that's actually doing the A to B format conversion. I was going to show you, but apparently Reaper hates me right now. So, but anyway, as I said, this plugin here is made by Blue Ripple Sound, and it's just kicks out a coincident stereo pair out of the sound field. And this is a very, very common technique. In fact, even going back to the hardware ambisonics decoders, the 1RU unit we have here, the hardware one that predates all the DSP, will do this exact process as well. One of the other fun things that we can do is run things through a binaural decoder. I was going to play this for you so you can see sort of the difference between the stereo pair and the binaural, but we're not getting stereo out, which is sad. This is a standard binaural it should be a binaural encoder. I don't know why they call it a decoder. Anyway, from IEM, there are a crap ton of ambisonic plugins out there, and some of them are really great, and some of them are okay. I don't think there are any bad ones. Anyway,
I could make a bad one. Maybe it's called a binaural decoder because it's decoding from the ambisonic format into a binaural format.
That could be. In a lot of cases, a lot of binaural plugins actually do use ambisonics as an intermediary layer. Like I said, because especially if you're doing head rotations, it's very, very convenient. And also, when you're doing binaural decoding, the decoding through ambisonics lets you encode your sound sources into ambisonics, and then use that as a translation layer for however your binaural convolution is happening. Because binaural convolution has to happen at discrete vectors. And so you can draw the discrete vectors out of the ambisonic sound field far easier than trying to interpolate each individual sound source, which is computationally expensive. Because then you have to do binaural decoder at each channel instead of one at the end. And then finally, the virtual microphone thing. And this one I think I can demonstrate because it only matters in mono. So this is a virtual microphone plugin, again, by Blue Ripple Sound. It's out of the same series. It's a fun, convenient one. Are we getting sound? Cool. So I'm just going to point the virtual microphone straight up. So in fact, let me go back to my slideshow real quick. This recording is actually about to play for you. And that is a choir, as we can see, standing around a Rode NTSF1 ambisonic microphone. This is actually the recording I'm about to play for you. Reaper. There we go. And there's the plugin. So right now the microphone is aimed straight up out of the choir. And of course, the choir's standing mix, so panning through the choir isn't quite as what's the word, impactful as other things. But there's a lot of interesting things you can do with this technique. I did a concert a couple of years ago where we were on a very limited setup time, and I put a sound field microphone above the conductor's head, just out of reach of her baton, and I was able to use some fairly aggressive virtual microphones in lieu of string spots by aiming them down the string sections to help reinforce the smaller string sections that she had compared to her winds and brass. So we also got the winds and brass to sit further back.
Let me make sure I understand. So one sound field microphone, and then you say, all right, so with that I can have an omni or a bidirectional microphone. I can also make out of that microphone, in addition, in parallel, so a microphone that's pointing at the first violins and a microphone that's pointing at the cello. So for the price of one tetrahedral microphone, you can make many microphones.
So an example of this is the virtual microphone array I did a couple of weeks ago for our choir recording. As you can see, our choir is out where the audience usually sits. We don't have any microphones hung there, and they're very, very distributed and very, very scattered. And as we know, if I was simply to turn our main stage array around, I'd only be getting the first few rows of the choir, and then these people, close to the camera would be lost just by sheer virtue of distance. So what we did is we got 3 of the ambisonic microphones. These are Rode NTSF ones. I have all 3 of them are, I think. Yeah. And we put them in different positions over the choir. And we were able to matrix out virtual microphones that basically sort of grab each region of the choir, and then we parted out each region with individual virtual microphones that we could then mix individually. And the end effect is that we were able to get a very intimate, tight choir sound without, with the choir standing 6 feet apart per person, in the audience area. And that is this other Reaper session, actually, to give you an idea. So these are the 3 virtual microphones, or the 3, real ambisonic microphones coming in. And then if you look down here, everything from vMic L1 over to vMic C2 are virtual microphones that I have matrixed out of the ambisonic microphones. That seems, sorry, wrong DAW. I don't know why these are all record enabled. So if I come over here and I grab these Omni flanks, so the Omni flanks are the pair of microphones that are hung over the stage where we would normally record the choir from. Which isn't a bad sound. We're missing a lot though. This is just the ambisonic array. We were able to capture a lot of the detail that the stage mics would have missed, especially with the choir wearing masks. We were able to get some of the consonants back in and solve a lot of other detail intelligibility issues. The other nice thing is the choir threw some curveballs at us, like people up in the balcony, and we were able to work around that. It wasn't in this concert. There were 5 concerts over the course of the weekend, but we were able to, work out more virtual microphones from the ambisonic ones that were simply aimed up into the balcony and mix those in. And so this setup gave us a lot of control over the sound of the choir without having to put up, a lot of microphones and have a lot of microphone stands and everything in the way, because this was video broadcast, which was the other nice thing about doing it this way. Questions about this? This was kind of a niche use of these.
I think that's really a fascinating approach. It's a lot of work in post, I suppose. But at least you have the flexibility, right?
Yeah. Well, actually, we mixed live out of Reaper. So I was sitting there with my mouse and having all the fun.
Wow.
In fact, we're about to do it again, something similar to this a week from tomorrow. We're probably going to do another similar thing in another hall with a similar situation. It's nice that DSP has come far enough along for us to be able to do these kinds of things. The other thing, this is from a recording this picture is from a recording I did of a wind quintet. Using 2 of the ambisonic microphones in ORTF. And this is something that Lynn Markowitz, I think his name is Markowitz. I can't remember now. Anyway, the gentleman who runs Core Audio, who makes the Tetramic, which is a very, very nice ambisonic microphone. And he also makes the Octamic, which is a second order ambisonic microphone. I think it's the only second order ambisonic microphone on the market. He's been doing experiments with using ambisonic microphones in place of real microphones because of the stability of their polar patterns. He's been doing all kinds of interesting measurements with his Tetramics, Octamics that he builds. Comparing them to like real cardioid microphones. And he's found that the virtual microphones taken out of a sound field microphone actually display a more even cardioid-like response throughout the entire frequency range compared to real cardioid microphones. And so for a recording I did, I gave this a try. I didn't feel any appreciable difference personally, but I think especially for a hanging array in a wider stage, I could see where the ability to tweak the width and angular display and directivity patterns of the microphones would be helpful, especially if you're familiar with the work of Williams and his the stereophonic zoom and all of his measurements he's done with the interrelationship between polar pattern and width and angular splay.
I have a question.
Sure.
So with these sound field microphones, do you have to worry about on-axis sound? I mean, how do you deal with that? Because I know with an ORTF pattern, right? I mean, one of the downfalls is if you point one of those microphones at something, well, that's on-axis, and that's going to skew it all.
On-axis is whatever direction I tell it to be, which is the nice thing about using them. So if for this particular recording, ORTF actually worked really well because of where the ensemble was in the room compared to the microphones, and the room has a very nice sound. I used this somewhere else as well, and I remember playing with where exactly on axis was until I found something that sounded nice. And that is again the benefit of the using the ambisonic microphones as a stereo pair is you can hang them, and then if you need to readjust sort of exactly where they're pointed, you can do that in post in software, and so they can be pointed in any direction you want, so you can redefine the stereo field through the microphone, and if you have one of the nice motorized bars, of course you can also play with the separation of them, but those are expensive. But yeah, the nice thing is, like I said, is the on-axis is whatever direction you tell the software is on-axis, which has been very helpful in cases. Yeah, did that answer your question? I feel like I kind of rambled.
I think so. Okay. Maybe I just have a misunderstanding, because I just think if one of those capsules is pointing at something, there's hardly getting
I see what you're. Okay, I see what you're saying. The arrangement of the capsules is the arrangement of the capsules and the calibration of the capsules that they use keeps it so that the sound transfer on to off axis is even enough that there is an even transfer of magnitude from capsule to capsule, so that you don't feel that like you would with ORTF. Because the issue with ORTF is the ORTF is so wide, it's 110 degrees, which was the reasoning behind NOS at 90 degrees, is that unless you're super close to the array, it is an even angular transfer from capsule to capsule. So yeah, with the orthogonal spacing of the capsules, it's a much more even transition from capsule to capsule. Yeah, I understand your question. So I mentioned higher order ambisonics a few times. There is an infamous picture that I will show you to give you an idea of what these higher coefficients look like. So the top line is your 0th coefficient. That is a graph of what your omni-channel would be. And on the second line would be your in this particular ordering would be your Y, Z, and X channels. And if you're looking at this, the white bulb would be your positive polarity orientation, and then any sound on the black bulb would be polarity inverted. And the next line down would be your second order coefficients. Those are graphs of what they look like. And then third order going down even further. And you see how each time you start adding more and more coefficients. And by using all these combinations of the polarity and polarity inverted lobes from each, from each increasing order, you can increase your angular precision so that a third order virtual microphone would have a much narrower angular precision than a standard cardioid, without having to have the rear lobe that we would associate with a hypercardioid. The other thing that happens as you increase your ambisonic order is your effective sweet spot for loudspeaker reproduction does increase. At third order, I think it's roughly the size of a human head. That sounds right. At third order, it's a usable size for one person. There is some deprocessing sleight of hand you can do to increase the sweet spot size for like group listening on loudspeakers, but you trade off spatial precision with that. That is 9 channels. I thought I was off by 1 when I said 8. Yeah. Where was I? So yeah. So
you were talking about a group listening on loudspeakers. So like an electroacoustic concert.
Yeah.
Everybody's grouped out or spread out in the space, or it used to be, and we have speakers surrounding, and then someone has an ambisonically encoded file they're going to play back for whatever configuration we have. Unless we're at some high order, that's probably not going to work out so great for the people not sitting in the center, right?
Yeah. Which is where you get into wanting to push the speakers back, constrain the audience as much to the center as possible. Like I said, there's some sleight of hand. It comes with the trade-off of angular resolution. But yeah, and so you do want to try to tend towards the highest order that you need to use the application you're using. But I mean, as you can see, the number of channels you're dealing in ambisonics increases quite drastically as you go up orders. So third order does tend to sort of be the cutoff point of where you see a lot of people working. And in my opinion, ambisonics tends to work better if you're doing binaural things. That's why it has a lot of use in virtual reality. That's why YouTube and Facebook are using ambisonics for 360 video. Anything where it's headphones, especially with head tracking, because it's so easy to turn the sphere. It's a magnetically solved problem.
Do you think it's advantageous enough, the higher orders, when we're using headphones, that those companies will eventually move to second or third order, or do you think there's no point in that and they should just reduce the file size?
I think Facebook already allows second order, I know there was talk of second order on Facebook at some point. I think the push will be towards third order. A lot of video game engines, I think, are running at third order now. That's been towards where the push for a lot of that has gone, and I think I think that there's enough benefit of going to third order that it'll happen. The big drawback is it's very hard to record third order directly with a microphone. And that's the big driver, is that for a lot of video content, especially on Facebook and YouTube, people, we're lucky if we see spatial audio with 360 video at all. I'm kind of disappointed the number of like 360 orchestra concerts and stuff like that I see on YouTube that are headlocked stereo.
The reason we wouldn't have third order microphones is because they would need 16 capsules, right?
Right. And I know of one that does exist. It gets to be questionably expensive, but there's some cool stuff they're doing with it. That's why I actually mention it here in a second. I have a list of it. So, actually, like doing ambisonics. On the software side, I don't want to leave without giving you some places to look at things. So the Blue Ripple Sound, the O3A Core VST pack they have is free. They're great. They're great plugins. I use them all the time. I've used them for years. They have a lot of paid stuff as well that is brilliant, brilliant DSP processing. They do some really cool ambisonics things. But they do have a set of free VSTs that work up to third order. I highly recommend, especially if you just want to like kind of jump in and play around with these kinds of things. And you have everything from encoders to decoders to it's a little bit of everything. They have ambisonic meters. It's a fun package. A good paid one that I've started using a lot is from Deer VR. It's Deer VR Pro. It's a VST plugin. Really nice, really full featured, and they do binaural translation in their plugin, and it's excellently done. Of course, binaural translation is sort of its own world. But doing a lot of stuff in ambisonics, tends to, because of the sweet spot problem, tends towards binauralization. So it's hard to do a lot in ambisonics. I'd be worried about what kind of binaural encoder you're using at the end of it. Sparta has VST, and I think they have max externals. I could be confusing with someone else. There's also SPAT, but I think that's paid and kind of expensive, if I recall. Although their max externals might not be. Probably just their VSTs are. But Sparta gets used a lot. Their VSTs are wild and full featured and completely confusing. That's a great learning curve to overcome because they do all kinds of crazy things. I feel like I left one off my list. Oh, in Max. God, was it? The ICST, and there's the HOA externals by, was it ICMC? No, ICSC. IC. There's too many I's in electronic music. Anyway, HOA, yeah, it's there. If you search for HOA Max externals, you'll find them. I lived on those in my masters for the ambisonics work I was doing. They're great. Yeah, the ICST ones are pretty solid. Yeah, HOA Library too. There it is. And for microphones, of course, the one I showed you is the NTSF-1. I have two of them in my personal collection. I have not regretted the purchases. Ball State has one. I got a couple of friends that have them. They're great, and they actually come with a Rycote ball that fits over the capsule array. Like standard, they come with it, and they have the cap that fits over the ball. So they really did rig this thing out for field recording. I've actually used mine outside. It works fine. It's great. A great microphone. If you have money to burn, there is the Sennheiser Ambio microphone. I never used them, never touched them. I just kind of looked at the price and noped out of that because I'm poor. People who have them swear by them. I see them around, but I have no personal experience with them. And then Core Sound has the Tetra mic and the Octo mic. The Octo mic is a second order ambisonic microphone. They're great. Facebook Facebook Reality Labs actually owns a crap ton of them. I think it's like they were doing these experiments with like 32 of them in an array trying to capture like 6 degree of freedom impulse responses or something. It's wild, but yeah, you see these microphones around. They're really, really well put together. The guy who makes them, he's actually very active in a lot of spatial audio groups on Facebook. He's very easy to reach and talk to. And the microphones are great. And there's the MH Acoustics Egan mic, which is a third order microphone it's basically this giant ball with a whole bunch of capsules. I don't think I've ever seen it used for music. I see a lot of people who do acoustics research with it. And finally, there's the Zilia ZM1, which is a third order microphone. And that company has some really interesting VR things they're doing. They're totally worth checking into. They've got this system they sell that uses as few as 3 and up to as many as you can afford of these little third order microphones. and you can actually put them throughout a room and then translate it into a 6 Degree of Freedom VR experience where you can walk through the room and automatically recalculate what it's supposed to sound like where you're standing within the room. It's pretty wild. Yeah, that's what I have. I am happy to answer questions. I know I'm kind of at my time.
Wow, thank you very much. I mean, I think we always learn something new when you present, so that was really good. I really enjoy the idea of the virtual microphones as being something that's not as, I don't know if that's how people normally think of ambisonics, but that is a good way to think of it, and certainly a useful way for a recording arts application. And I will let some other people ask questions if they have them.
Cool. I mean, the virtual microphones have been great for us. We've gone to streaming everything because of COVID, and we've been using our spaces in weird ways, like using the audience area of our main recital hall. And the flexibility of the virtual microphones, being able to throw up an ambisonic microphone and then get whatever we need out of it, has really helped us sort of roll with the punches as they make decisions, moving choir people around, putting people up on the balcony, all kinds of crazy things. And it's nice to just be able to sort of re-aim all the microphones without having to, walk out there and physically move stuff around. Makes life easier.
I guess I have one question that maybe you have advice about. So
Sure.
When we spatialize things with ambisonics, so now I'm thinking about composing, for instance, and then using spatialization to move my sounds in the space. It's often the case with ambisonics that there's a lot of spread, right? Because we are dealing with something which relies on phase cancellation, in essence, to put a sound where it belongs. And I don't often see in plugins I use the ability to reduce that spread. Is that something that exists? I noticed like a sharpness sort of knob in one of the plugins. I didn't know what that really meant.
There's two routes you can go with that. Of course, the amount of spread you get is directly related to the ambisonic order you're working in. Is the first thing. The other thing is that there have been some recent breakthroughs in spherical harmonic beamforming, which is a completely different approach to casting out virtual microphones from the matrixing approach I showed. And I'm still trying to get my head around exactly the math they do. I had followed beamforming as well, and I'm also not a mathematician. But that allows the creation of very tight polar patterns, with minimal spread and with minimal antipolarity information. That you can do. I think Rode incorporates it into their plugin that they use with their microphone. I think that might be part of what the sharpness tool of the plugin I was using is. They can use a smart thing. But the big thing I would say is that the amount of spatial spread you get is going to be a direct consequence of the ambisonic order you're working at.
Okay, that's a great advice. So I think now I'm going to have to call the meeting. I really appreciate you doing this for us. It's always great to hear from you. And
mind if sorry,
go ahead, John.
Mind if I answer Andrew's question real quick?
Oh yeah, sure.
The question chat. The ambisonic microrecorder made by Zoom. I've only heard people talk about it. I've never used it myself. I think I've heard that it's fine if you're not aiming for like high fidelity music experiences. If you're just trying to like put it out in a room and like record through sounds like or something like that. It's used a lot by like run and gun filmmakers is what I've typically seen. And so if 250 is what you've got as an entry level point, it could be a lot of fun. I mean, a mic's a mic, right? But I never heard anybody say anything bad about it. Just that I don't think people would consider it for like, recording an orchestral concert is something you were going to seriously release. Is that? Yeah. Okay.
Okay, so
Sorry.
so with that, I'm going to end the meeting, but I will say that Jeff is on our Discord channel for you local students that are on our Discord channel, and also can be reached by email, obviously, and is always willing to answer questions and be involved. And with that, I will say goodbye to everyone on Facebook first. So let's see here. I'll stop that. And now I'll say goodbye to everyone
Thank
on
you.
YouTube and on our Zoom meeting.
Nice to see y'all, guys.
Talk to you later. Bye.